Good morning, good afternoon, and good evening, everyone. Thank you for joining us today, and welcome to the DAS RCN webinar on instrumentation. I'm Casey Adderhold from Incorporated Research Institutions for Seismology. IRIS is a consortium of universities and an NSF-funded science facility operating programs that enable Earth scientists to perform advanced research in geophysics, particularly in seismology. This webinar will be recorded and archived on the IRIS Earthquake Science Presentations webinar YouTube channel. Should you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the Q&A box, not the chat box, on your Zoom control panel. At the end, we will read your name and question to the presenters. If similar questions have been asked, we may combine or skip them. If the webinar happens to crash due to Zoom or internet issues, we will reboot it. Just click the webinar link again. Automatic captions are available to be turned on and off on your Zoom control panel. And I will make sure that that is enabled. Use of distributed acoustic sensing is rapidly expanding in our community, prompting the initiation of a research coordination network to facilitate workshops, tutorials, and other opportunities for sharing ideas and resources. This is one in a series of webinars on different topics within distributed acoustic sensing. I'm going to pass this to Dr. Yingping Li now to get us started.
Good morning, good afternoon, good day around the world. And thank you for joining us today. My name is Yingping Li, and I am a co-leader of the Instrumentation Working Group of the NSF-funded DAS Research Coordinator Network. Today, we will hear from some of the vendors participating in the group as a part of the series of webinars showcased by the DAS vendors and DAS service providers. This will establish a platform to bridge users and the vendors, leading better communications among the DAS societies. We welcome others to get in touch if they would like to present on one of these in the futures. So our first speaker today is David Hill from Sintela. His presentation title is Onyx Sensing Unit for the field DAS data acquisitions. So Dr. David Hill is the co-founders and the CTO at the Sintela, a UK-based company specializes in the research, develop, and the manufacturers of distributed fiber optic sensing systems. Since 2005, David has taken a leading role in the development of DAS and its introduction across a wide range of industries. He is currently working with partner companies and organizations to enable them to fully exploit the potential of these technologies. So right now I hand over to David.
Thank you very much indeed, Yingping and Casey, for arranging this webinar today. As I say, my name is David Hill, and what I'll do is introduce the technology, the Onyx technology we have, which is DAS. But first, I'd like to start with just showing you a little bit about who Sintela are. So the founders of Sintela have really been at the forefront since 2005. Myself and my colleagues, that's when we really first started to build and apply DAS technologies. Predominantly, first it was for the oil and gas industry, but latterly we started to expand that into other areas such as transportation, rail, road, security, and other areas. Sintela itself is really a leading industry supplier of distributed acoustic systems to customers and specifically our partners that we work very closely with across multiple industries. So as I say, oil and gas, transportation, security, and there's a growing other market areas that we're investigating at the moment. And really what we're focused on is enabling people with the technology. We spent at least a decade really showing people what DAS could do and educating the market on the potential of DAS. And I think we made a pretty good job of that. And now it's a case of moving to the next phase, which is enabling our customers and our partners with the technology so they can go ahead and fully exploit it. This is probably about the 8th DAS system that the team has actually put together. So it comes with a huge amount of experience in building these systems. And it's very much designed as an open platform that can be tailored to individual industrial applications, be them oil and gas, rail, transport, whatever. It's a quantitative system, so it accurately measures the amplitude, the frequency, and the phase of signals. And and of course, like all DAS systems, it acquires that information along the entire length of fiber. In this particular case, this unit actually supports 2 fibers. So you can have 2 channels running simultaneously from this unit. Everything in the system is fully software reconfigurable. So there's no hardware, there's no fixed settings or gauge lengths, pulse lengths, sample intervals. They're all completely controllable from the software. So as we say, it's software defined sensing because you can change it at will if you need to. So a bit more about the detail. This is the Onyx is our currently commercially available product. We have others, but this is the one that's actually freely available outside of our partners. This, as I say, can measure 2 fibers, typically 50 kilometers, 31 miles operational range on 1 fiber. Can actually go longer than that, and I'll discuss that later. So from 1 box, you have 100 kilometers or 62 miles can be interrogated from 1 box. As I've mentioned, it's fully quantitative phase-based measurements, which is very important if you want to do seismic types of measurements. It's got industry-leading sensitivity on standard fiber. So all the specifications we give are just using standard SMF28E fiber. However, and those specifications, if you compare them, they're very comparable to other people who are using engineered fiber. We can actually use engineered fiber as well. We've tested about 4 different types of engineered fiber, and we get the gain in performance that is suggested. So if you want more sensitivity, 10, 15 dBs, and you're prepared to use engineered fiber, then the system is fully compatible with that if that's what you want to do. But our remit is very much to stick with standard fiber as much as possible because that's what's out there in the real world. So that's what we tend to use. It's got a fully integrated processor on board, so there's no separate unit to this. There is no separate processor you need. Everything is included within the box itself. It's a very high performance processor in there, and it allows us to do at the edge processing, which we do. We have an automated optical setup for the box. So one of the things that's always troubled these DAS systems is they can be quite complex to set up. And I think there was a comment many years ago is please take the PhD out of the field, in terms of setting these up. Now, there's plenty of PhDs, I'm sure, will be listening to this call and will want to be in the field and want to run the box. But for those who don't, it's a 1-button press and you can pretty much set all of the optics up and it's fully configured. And importantly, it's fully controllable over the internet, so it's fully remote controllable. Every aspect of this can be accessed through a web-based interface. So you can retrieve data, you can control every single aspect of the operation of this box if you have an internet link. And we, from our office in the UK, we have access to many boxes that we, of both our own and customer boxes that we maintain and support should they need support. So during COVID, for instance, it hasn't really been a problem for us because we've just been able to log in and support them. Triggering on the box, we can also support triggering. So we have GNSS signals can be put in the box as well as NTP and external clocks. So for timing synchronization, we have access to UTC and we can get 1 millisecond accuracy from a GNS GPS signal using a GPS antenna connected to the back of the box. Or we can use external triggers, and we have the seismic interface device you see there, which allows us to put in triggers. This one's actually a 2-channel system, but we have 8 triggers can actually be put into the system, and we can use all of those. And they will provide plus or minus 10 nanoseconds accuracy. What that allows us to do is we can do good, very good seismic correlation and stacking, should that be required. And you'll see the little video there that's just running through a series of VSPs that were gathered on this fiber. And you can see the good correlation between all of those and the correlated stack at the end. Now that's only really achievable by a quantitative system and very accurate timing in the box, which is available. So very much the Onyx was designed from the outset, designed for field operations. So it's a small form factor. It comes in a 19-inch 3U enclosure. Sits inside a rack. It weighs 37 pounds or 17 kilos. That's an important point because in its case, you can still take it on a plane as hold luggage. And we can take this, you don't need to do special shipping arrangements. You can carry it on commercial airlines should you wish to do so. It's very low power operation, so it takes less than 100 watts of power. This means that it can be powered from a fuel cell, for instance, in a remote location, or harvested energy from wind or solar. So solar power, roughly 4 feet by 2 feet, would give you 100 watts of power, enough to power this unit in a remote location, should that be something you wish to do. It's got removable storage, so it has up to 16 terabytes of memory that can be installed in the front of the box, and that's on 2 SSDs. And external storage can be added should you decide to do so. So if you wanted to add a RAID, for instance, RAID unit for more storage, then of course that's available. It has a very wide temperature range. It goes from 23 degrees Fahrenheit to 122 Fahrenheit, or -5 to 50 degrees centigrade. But that's purely passively cooled. So we don't have any fans on this unit at all. It's an entirely passively cooled unit. And the reason we do that actually is because one of the biggest failures for DAS instruments we've found over the years tends to be mechanical components like fans, clogging up with dust and dirt and so on and so forth, and therefore need to be maintained. Without those, the maintenance regime is very, very long indeed. You don't have to maintain these systems very often at all. These are IP50 protected, so they're protected against dust, and as I say, they're sealed fanless design. So really, it's almost a fit and forget technology, as I say, minimal maintenance. And finally, it's safe to operate. It uses a class 1 laser on this box, so there are no particular safety risks of using this. Just want to go back a second just to show you the front. I forgot to say, so here is where the SSDs fit in the front of the box, just under a flap here. And on the back, you've got the interfaces. So we've got a dual redundant power supply for reliability, and it doesn't strain the power supply, overstrain it. 2 outputs, an auxiliary input for the triggering, and a GNS antenna goes in there. So that's all you have on the actual box itself, as well as 2 touch screens at the front. So you can, as I say, it's fully controllable over any web connection. But should you desire to control it directly from the box, then you can do. You don't need keyboards or screens to do that. You can operate it solely from the box itself, should you wish to do so. Right, the other things that you can get from this is it has an inbuilt OTDR, so you can run an OTDR on both fibers directly from the box. And that means should you have a fiber connected in a remote location and you're worried about something like hydrogen darkening, for instance, or potential damage to your fiber, you can, from your office, you can run an OTDR on that box and see what the results are. And of course, those are saved so you can compare them with previous OTDR traces as well and see if there's been any difference. Same thing goes for the performance of the box. So all of the system vitals, the temperature, the voltages, the amps, the currents, everything, including any shock and vibration. We have an accelerometer in there as well, see if it received any significant shock. All of those are constantly being recorded and either stored on the box, or if you've got a web connection, sent to the cloud, so that they're always accessible and retrievable. The specification specifically, as I said, where we say 50 kilometers as our standard range. That's using a gauge length of 6.4 meters along it. With longer gauges, of course, you can go longer than this, and we've achieved in a lab very, very long ranges indeed. But you have to kind of pick a point of what is a typical gauge length and what is the kind of measurements that you expect to see at the end of the fiber we want to measure. And so we specify it in this way, 50 kilometers, using a 6.4 meter gauge. The minimum gauge length is 3.2 meters, maximum is 40 meters. Sampling interval is minimum is 1.6, and the sample rate, the minimum is 1 kilohertz, and it goes up to 40 kilohertz. All of these are fully software configurable should you wish to do so. The acoustic range, typically we stick in a 1 millihertz high pass filter in the system, but that's really just to get over any DC bias. But should you wish to see that DC, you can remove that 1 millihertz filter. As I say, fully software configurable, so you can put whatever filter, high pass filter you want at the front end. And at the back end for 100, for a 100 kilometer long fiber, you'd be looking at a 500 hertz acoustic bandwidth. For a 2.5 kilometer fiber, you'd be looking at 20 kilohertz acoustic bandwidth. So when we look at the actual sensitivity, the kind of sharp end, I guess the most important bit, you're looking at minimum detectable signals at the front of a 5 kilometer fiber using a 6.4 meter gauge. You're looking at minus 80 dB rads per root hertz, and that's taken at the 10 hertz position. And that's equivalent to around about 1.5 picostrain per root hertz. If you go out to 50 kilometers, at the front, you'll measure about 60 dB rads per root hertz on the same system. And the corresponding dynamic ranges, as you'll see here, they're very large dynamic ranges that are measured at these are different spot frequencies, 1 hertz, 10 hertz, and 100 hertz. But as you can see, large dynamic ranges are achievable. All those measurements, everything we do, we base back to CFOM test results. So we have an automated CFOM test rig. Those of you who are not aware of CFOM, it's really the only industry body that's actually put out a specification of how to test DAS systems and how to compare them like for like, because that's always been a bit tricky to do. So CFOM is always a very good resource should you want to compare DAS systems. And we produce reports on all of our different combinations. And as I say, that's fully automated system, so we can turn these reports around very quickly. We've also got, this is our CFOM testing rig, where the box sits in an environmental chamber on a vibration isolation mount. We also have environmental chambers for doing temperature and humidity tests. And this is just one of our units sat in just in a rack undergoing factory acceptance testing. So from those CFOM results, we're able, as I say, to take very good measurements. And I want to just show you some of the sensitivity results that we get. So we actually can run the unit, the Onyx, in 2 modes. Mode A is our standard processing mode, which converts the backscattered optical signals into an acoustic signal. But we also have what we call mode B, which is an enhanced processing mode. It's developed to improve the low frequency response in quiet environments. So for kind of seismic measurements and earthquake measurements, it's been especially useful. You can run these on, you can run mode A on one fiber, mode B on another fiber. You can run mode B on mode A on both fibers, whatever combination, including running them concurrently on one fiber. So you can take one fiber and get an A and a B output if you so desire. Now, why it's important is that there is quite a significant advantage of using mode B. What we have here are the noise plots for the system. So this was recorded on a 5 kilometer fiber at on a standard fiber at 5 kilometers, 20 kilohertz sample rate, gauge length of 6.4, as well as a sample interval. And the gray plot here gives you the response of the system, the noise response of the system of our standard mode A, and this is mode B. So as you can see at the very low frequencies down here, down to about 4 or 5 hertz, you're getting a huge improvement in the low frequency noise. Now, if we convert that into seismic units, this is actual velocity. So on this plot here, what I've plotted is this is the Peterson low noise model that you have here, which I'm sure some of you will be familiar with. This is the red line here is a response of a Geospace 1 geophone, so standard 10 hertz geophone that you'd expect. This is the standard mode that we run, mode A, and this is the enhanced mode. So you can see the huge improvement you get in noise floor at the very low frequencies. This is obviously a log scale frequency along the bottom. Now that does come with some caveats for the current design, the current commercial version. So mode A can be used on full fibers over the full 50 kilometers plus length, and has that 1 millihertz high pass filter cutoff. And it has very high dynamic range, whereas mode B is currently limited on the commercial box to 12 kilometers on either fiber. So up to 24 kilometers you can use this mode on. It's got a 0.2 hertz cutoff and a slightly reduced dynamic range. So it was originally designed for seismic applications such as VSP and microseismics, but it's also found really good use in earthquake monitoring. So this is the earthquake, the Fukushima earthquake we recorded earlier this year. We were about 1,000 miles from the epicenter in the south of Japan. And what you're seeing here is the waterfall plot. This is just car noise on the back. So these are vehicles which we see everywhere. And of course you can see the P and the S wave of the earthquake coming through very, very clearly indeed on this system. So it's got very, very significant advantages that running mode B for these types of measurements. I think it's worth mentioning the DTGS, so distributed temperature gradient sensing as well. For those of you interested in temperature, at frequencies below 1 hertz, the response of Onyx is very sensitive to temperature changes. And by low pass filtering this data at low frequency, we can provide a channel, some data out of distributed temperature gradient sensing, so changes in temperature. Since the Onyx is a phase-based quantitative system, we get minimal low frequency drift, so it provides a very reliable measure of this along each fiber. And to give you an indication of the kind of sensitivity achievable, the first plot here shows 8 separate channels along the fiber being measured and running through a temperature cycle. The plot here on the right shows the mean of those channels in blue. It shows a thermistor output in red here, and it shows the fitted curve of the response in the orange line. So we're getting 13 millikelvin per second response on the DTS response, which is extremely fast and very, very high resolution. So there is a difference between those of you who've used distributed temperature sensing. That obviously gives an absolute measure. Typically you can get measurements for about half a Kelvin over minutes of integration time, whereas with DTGS we're measuring rate of temperature change, and we're getting millikelvin in milliseconds. So there is a clear advantage there for those types of measurements. Software and algorithms. We develop all our own software in-house. We've got a dedicated software development team. The team have been developing DAS software for over 15 years, so they're vastly experienced. And we do everything, the algorithms, the processing, the user interface, the user experience, that's all built in-house. And as I say, it's all a web-based software. So the software actually runs on the box itself, and we just do a web connection straight to the box wherever we are. As long as we've got the URL for the box, we can log into it. Obviously, it's all secure. It's got multiple security protocols on it, but we can log in and we can access these pages and gather the data. So you're seeing a page here. This is a well, a down well response. This is vehicles in a city. This is a pipeline, and this is just tracking vehicles on our display through an urban environment. This is all software that we've developed. We have a processing chain that we can use, so we can actually set up the processing chain to put in our own algorithms and other people's algorithms, and output raw data, HDF5 or SegWi. And we offer the APIs, and the ICDs are available for users to put their own software on this. Some of the things algorithmically, we're looking at working with some of our partners in developing heuristic and machine learning algorithms. So this is taking a microseismic event. This is the raw data, and running through some of our algorithms. This is the automated microseismic detection that we're now achieving through our algorithms that we're running. As you see, it's pulling out a lot of data you can't really see on the raw data plots. Training and support. Training we provide online or in person. We have a Sintela knowledge base, which allows you to access all of the manuals, but we also offer online support. So certainly our university customers, we're more than happy to pick up the phone, log into the box remotely, and help our customers set the box up optimized for their particular experiment or trial that they're doing. So in summary, hardware, small form factor, lightweight, low power, and built-in processor, as well as storage. The performance is quantitative, over 100 kilometer range with industry-leading sensitivity, and all the parameters are software definable. Processing can be done at the edge within the box itself, no need for a separate unit. And we have heuristic and machine learning based algorithms that we've developed, and increasingly our partners and customers are putting their own algorithms on the box as well. Software has advanced capabilities, it's web-based, and the APIs and ICDs are available to our customers should they wish to do so. And final point is, this is as I said at the beginning, this is our commercially available product, but there is a continuous development with our partners looking at a range of next generation distributed fiber optic sensing products. Thank you. That's it. So any questions?
Thank you so much for David's presentation, very informative. So any questions? So we may have a few quick questions, now move to the next speaker. And then finally we have some kind of the panel discussing. So if you have any questions, you can type in or just raise your hand. Yeah, how do you, one question from Barry Freefield. How do you connect with the external storage, SFP or USB?
It can be, through SFP. So you can either use a wire Ethernet or a fiber Ethernet up to, I think the fiber one goes up to 100 kilometers offset if you wanted to do that, or USB-C connector. So either way.
Any more questions?
Is there any concern about the putting the system into hold baggage for airlines? Has it been tested in its box and it's
no, we do it all the time. So no, it's not really an issue at all. It comes with a hard carry case, and that is just under the kind of 37 kilo weight limit that the planes have. So it's oversized luggage, if you like, but airlines will actually carry it, and it has nothing on board that is specific that airlines are worried about batteries and things like that. There's nothing there that needs to be removed. So yeah, you can take it wherever you want.
Great, thank you.
David, I have one question. You have shown that you have the traffic recording, but then you also recorded the earthquake in Japan, right? So what's the earthquake signals compared to this traffic noise? What's roughly the signal noise ratio?
They're very comparable, actually. I mean, that was quite a big. Obviously, the Fukushima earthquake was quite a large one. I think it's 7.3. We were about 1,000 miles away from it at the time, but the signal to noise was. I can't give you an actual figure, but I know it's very, very clear. There was, it was comparable to some of the cars that we were seeing on the road.
Yeah,
so this fiber was a standard fiber. It just happened it was deployed right the way down a highway, and we just plugged into that, and that's what we were using for earthquake monitoring in this particular location.
Yeah, I have the question because we have showed see a lot of people just monitoring the trains and monitoring the traffic, but then if this is working, we can turn all of this railway monitoring as a seismic network, because you not always have a train, right? So when sometimes you have very strong train signals, but other places you don't have a train, you still can record an earthquake. So that could be extended network.
Absolutely, we see earthquakes all the time. So all of our kind of partners have got systems on railways and massive pipelines, transcontinental pipelines, and road networks around the world, and we're constantly measuring earthquakes. Unfortunately, from our customer base, then that's not what they're interested in. They're interested in the trains and the cars and what's going on. So those earthquakes are like, oh, that's interesting, and then throw it away. But that particular customer in Japan, they were interested in the earthquake, so they gathered that data and they're processing it. So it depends on what the interest is at the end of the day. But yeah, we see over my we've seen thousands of earthquakes. I mean, thousands of them all over the world. And unfortunately, you'll hate me for saying this, but we've just thrown them away nearly always.
Yeah, we can discuss this more, but we have one question here. So the GMOs is the machine learning capabilities, its commercial application that can run in the real time on the interrogators. I mean, for the microseismic monitoring.
Yeah, that's exactly what we've been doing. So we've been doing it. So it's all on the edge processing, and real time on the edge processing. So it just picks out the microseismics to automatically identify when they've occurred.
We have another question, Florence. Does the units come with some kind of the protocols for the streaming data in the crazy real time? Probably not the 2 kilohertz data, but maybe down sampling data.
Yep. So we always sample as fast as we can possibly sample, and then in the box we decimate down. So we can decimate to 1 millisecond, quarter millisecond, and typically for most of our seismic customers, that's what they'll want. They'll want it in 1 millisecond SegWi format. We can output it in HDF5 as well if required, or our raw format. So all of those formats are available. Typically, if you've got a very, very good internet connection, then yes, there is the potential of streaming this live, or certainly to the cloud. Most people, however, we store it on the box, and we can then retrieve it at a later date via an internet connection if that's required. So earthquakes, for instance, when an earthquake goes off, we've got about 48 hours of raw data recording, and therefore we can go back into the box, just go back to that section, highlight where the earthquake is, and say download that, and then that goes up to the cloud and is available to people to look at the raw data remotely.
Okay, thank you. So let us move to next speaker. So if we have questions, you can save for the end if we have the panelists discussing. Thank you so much for David. So our second speaker is Ricardo Arias from Aragon Photonics. His title is "That's a Successful Case with Chirping the Past Technologies." Ricardo's head of sale at the Aragon Photonics. The entry points of the companies are ready to listening, help, discussing, and collaborate with the customers and the partners of any kind. So I hand over to Ricardo.
Thank you, Yingping. Thank you, Casey. Thank you, Herb. And thank you, David, for your nice presentation. So I'm Ricardo Arias, Head of Sales at Aragon Photonics. And although I'm not the as technical guy as David, I will do my best to show you some slides about what we do here at Aragon Photonics related to sensing. But after I show you some success cases, mainly in Spain, why not? I will briefly introduce Aragon Photonics and our scientific partners. I want you to relate both Aragon and our partners from today, if you are not, you don't have this information in mind. And also our technology, which is different from conventional phase recovery DAS, is called the chirped DAS, with some clear advantages, and we'll show you also the specifications. So let's go. So at first, Aragon Photonics is a manufacturer of high performance test and measurement equipment since 2004 in Zaragoza. We were one product company, which is the BOSA Brill One optical spectrum analyzer, a high resolution optical spectrum analyzer. As you can imagine, we've been dealing with this kind of technologies since the very beginning. And we are experiencing a solid growing since 2015, when we started to diversify our business portfolio. We have three main characteristics. Let's say we manage innovation. All of our products have unique and patented technologies. And we have very high technical staff, both here, internal staff and the external staff that collaborates with us on a daily basis. We take care of our products a lot. We do all the manufacturing here in Spain, on site in our facilities. And since this year, we've been certified as with the quality control ISO 9001. Although we are a small company of only 25 people, we sell worldwide, already in more than 30 countries. And we have a strong network of distributors and partners all over the world. And one of the things that we are most proud of is our support, named as a JALI support, with a response for any doubt, any question, any inquiry in 24 hours. We have three business lines. One is related to the optical communications since 2004. Another one is related to solar instrumentation. We manufacture also an spectrometer and reflectometer for concentrated solar power plants. But the core of our business here at Aragon is related to TIFOS, to fiber optic sensing. Aragon Photonics is more than just a manufacturer of products, of high precision products. We have a strong R&D here, internal and external, and I want you to know who they are. We have scientific partners both for R&D in the technology, in the DAS, but also in applications, and that's why some of the papers that I'm going to share with you have been written in collaboration with our partners, and even without being us there, with external, even external from partners from this University of Alcalá, UAH, University of Zaragoza, of course, and the Public University of Navarra here. And people you might have heard about from Miguel González Herráez, who is the group leader in Alcalá, but also Hugo Martin, Sonia Martin, and Maria Fernandez. Probably you have already read a paper where they are co-authors of them, or the main author. And also I want to point out that our product, which is named the HDAS, is exactly the same as the chirped pulse DAS you are reading about, sometimes referred at CP DAS or CP phase OTDR. It's exactly the same. It's our product is the HDAS that we manufacture. And well, this year there is again an exhibition and huge conference, OFS 27, by the late of August, and we will be happy to be there to exhibit our HDAS and most likely something else new coming there. So some words about the technology, about the chirped DAS. Probably most of you you haven't heard about, and I encourage you to read some papers, a couple of papers. Pastor Grail's 2017, because this technology was born after this question: can we avoid signal fading in traditional phase recovering DAS? Let's try to avoid any kind of fading, polarization fading, or sensitivity fading. So that's why this technology was born. So we don't send just pulses; we send pulses that have been linearly chirped and propagated through the fiber. So as you can see in this picture, any strain perturbation on the fiber produces proportional local temporal shifts in the generated trace, and the frequency to time mapping induced produces a linear relationship between the trace temporal shift and the applied strain. This is our technology, and this has some clear advantages. The first one is that intrinsically this technology is linear and quantitative by hardware. No need of extra processing for doing that, or for reaching more kilometers of quantitative or linearity. It's all the reach is linear and quantitative. So, and as I said before, it's immune to fading points. And these are the two main advantages of our technology. So it's also low complex and high cost efficiency. You can ask for a quotation after. The SNR also is homogeneous from point to point along the fiber, and the sensitivity is because strains root hertz clear, or can be said also as a 1 nanostrain. And all the data is extremely raw. It's raw data, linear and quantitative, and everything is there in the raw data. So it's an excellent technology for seismic activity monitoring. It's good to know that others, such as Sintela, are capable of including the sensing unit in one device. Well, for the moment, we have two separate boxes, but this is not an issue when you rack the HDAS someplace safety and security, and you control it remotely. So it's long reach up to 70 kilometers here, calibrated at Aragon Photonics at the 1 kilohertz of sampling rate. But it's been also demonstrated, this equipment with a reach of up to 100 kilometers with 50 hertz by the University of Alcalá de Henares. The strain rate, but also relative temperature with a similar approach as Sintela. We call it spatial resolution, and it's exactly the same as the gauge length. It can be others under request, but the standard is 10 meters. The sampling resolution can be down to 1 meter, and the sampling rate is from 200 hertz up to 4 kilohertz. It can be perfectly remote controlled. It comes to the device comes with a GPS, with an antenna for synchronization. All the factory acceptance tests here at Aragon Photonics are done following the CFOM, of course, and it's also an open system for application developers. Some of our partners, they use as well as you in the scientific world, the raw data to the noise, the signal for or any other kind of algorithms. So that's the equipment. Now let me show you at least 3 success cases. One was the Cumbre Vieja, the La Palma volcano of last year eruption. I was there with my colleague Javier, the product specialist of the HDAS. We installed in a couple of hours the HDAS at the Center of Astrophysicists in La Palma, and we started to monitor over more than 50 kilometers of fiber optical cable. The first 3 kilometers underground cable from this particular center until the beach, let's say, and the rest is a submarine cable from La Palma to Tenerife. And we immediately started to record the data strain and raw data strain. And well, before seeing a rush hour that happened on the 17th of November, let me show you a video of what I personally saw. These fireworks at 4 kilometers of distance of the volcano. We were amazed by the lava reaching the sea from the main cone of the volcano. It was really nice to see this at night. But what we saw with the HDAS, we saw this kind of traffic. Sorry if this is in the axis are upside down, what you are used to. Time is in the x-axis, and the length measuring 30 kilometers. And we, well, our customers saw this. We saw something similar, but not rush hour, 17 minutes. And we could relate this information with the Geographical Institute here, National Institute in Spain, to the magnitude of the Earth, 0.6, 0.7, 0.9 can clearly can be seen without any kind of processing. This is just the HDAS when you turn it on and you don't apply any kind of software algorithm or anything. This is just plug and play. We saw that. And if you look at the bottom of the trace, then you can see that, of course, we were tracking the first 3 kilometers. We were tracking vehicles moving to the in the highway and some street roads close to the sea. And as a courtesy of the customer, which is the Technological Institute of Renewable Energy in the Tenerife Island, they sent us last November this couple of images with a P wave and S wave of these 2 earthquakes with a depth of 11 and 29 kilometers. The ITER, they have a paper, or at least a lecture in the European Union event in Vienna. So you are invited to follow them as well. I'm sure they will get in depth with all this information that I have just shared with you. The second case, also in Spain, also in the Canary Islands. It's been recently published in the Seismological Research Letters. The main author is Arantxa Ugalde, and other co-authors come from the University of Alcalá de Henares, and the title name is Noise Levels and Signals Observed on Submarine Fibers in the Canary Islands using DAS. So there were 70 days recording between Tenerife and Gran Canaria, over 120 kilometers. There were 2 HDAS units, one here in Tenerife, monitoring 60 kilometers from the island, and the other one was located in Gran Canaria, measuring again another 60 kilometers from Gran Canaria. They were able to track and to observe many things, and the first one, like the ships, vessels. Okay, here the spectrogram for one vessel in 11 kilometers from the coast of Gran Canaria when this happened. What else? Local and regional earthquakes as well, measured with magnitudes over 2, and all this information I think is public if you search for this paper. What else? Surface seismic events at a distance of more than 3,000 kilometers that were identified by the US Geophysical Service. And the most important thing, it was the very first time that hydroacoustic waves were directly observed using DAS. That's for the very first time. As you can see here in this picture, the last one was measured with the HDAS, and the first 3 ones were measured with local seismometer. And a third success case, which for us is we are really proud of, being in the Nature Communications by Williams. Probably some of you have already have a look at this name, distributed sensing of microseisms and teleseisms with submarine dark fibers. Williams and also some colleagues of ours of the University of Alcalá de Henares were in charge of this document. So essentially, there was a fiber optic cable, ocean bottom fiber optic cable in an offshore wind farm in the North Sea, the coast of Belgium, and multiple categories of signals were happening there. The first one, it was really impressed a teleseismic body wave from an earthquake in Fiji. Okay, 16,000 kilometers away from Belgium. So this the telegrams arrived to Belgium. Let's say although it was at a depth of more than 600 kilometers. I think all the data is also public for if anyone wanna play with that, and also the is were measured in the very low frequency band. I think it's written in the supplementary of this article. And also very important, the identification of oceanic and seismic signals. Okay, the ocean waves and the seismic waves, let's say, clearly different. Discrimination of the primary and secondary microseisms. Okay, please, after I finish, don't ask me much information about this because I'm not a technical guy, but I will be pleased to put you in contact with anyone. Okay, but I'm just I'm capable and able to understand this kind of waves. I've been learning a lot from communication, and also ocean surface gravity waves with asymmetrical dispersion. Okay, to an ocean current and energy imbalance between the seaward and the landward waves. This was also observed and almost quantified in this Nature Communication article. I don't know how much time I do have, but there are other publications where Aragon Photonics, together with our colleagues at the University of Alcalá de Henares, have anticipated, like these 3 ones. And the latest news is that these 2 ones, the first one, I think it was published just 1 month ago as well, from Williams, surface gravity wave interferometry and current monitoring with ocean bottom dust. Okay, where internal tides, okay, the internal tides were directly measured with dust, if I'm not wrong, first time. Shift this paradigm in mapping this kind of phenomena with sensitivity of millikelvin, with sub-hertz mapping, and of course 10 meters resolution over 100 kilometers. It's a new article that it will show very extremely stability in the long term with our technology, with the HDAS, with an accumulated error of just 3 megahertz, 3 millikelvin, 30 nanostrains after 1 month, more than 800 hours with temperature control inside a place that you will find out very soon. So if you have any questions that I can answer, I will be happy to do that. And of course, please follow us on LinkedIn, because we will be showing news very soon, specifically for the OFS 27 exhibition.
Thank you so much to the Ricardo's very nice presentation with a lot of good examples show the earthquake and the volcanoes monitorings. So if you have any questions for Ricardo's, please just use the Q&A. And also both David and Ricardo show their email information. So if you have further questions, you can continue contact with them.
Yeah, of course, I will be happy to share any article that anyone can be interested in.
So any questions from audience? So I have one of the questions when you show this volcano monitoring. So basically you have both fibers on the land, but also have the fibers in the oceans. So do you have any seismometers on the island that make a comparable measurements and a comparison with the DAS data?
Yes, there were several seismometers on the island. Indeed, since the eruption started, this customer of ours, but others researchers went to install more seismometers, and I'm sure that for this publication in 2 weeks, they will show and they will compare the results with the seismometers in land.
Okay, if we have no more questions for Ricardo, so we can also have if you have more questions for the David, so we can make the panelist discussing, but we probably make it a little short because the time is past 1 hour already. Also, Casey have make an announcement in the chat.
Yeah,
so
certainly.
that's yeah.
Yeah,
Okay.
I can go ahead and wrap up, but thank you so much to our presenters today. I apologize for my cat in the background. And yes, we do have another group of instrument presenters next month. So please go ahead and register for that event in June. But yes, thank you to Yingping for moderating and to David and Ricardo for their presentations today. The recording will be made available on the IRIS Earthquake Science webinar playlist. If you are interested in future DAS webinars, please join the DAS mailing list and check out the DAS RCN website. Thanks so much for joining us.
Thank you, Casey, for organizing this, and thank you, Herb, to supporting this activity.